Hello everyone, I'm Dan Deng. Welcome to this series of videos on 5-minute embodied intelligence. Through this series, we'll help you quickly build a comprehensive understanding of embodied intelligence in a way that's as accessible yet professional as possible. Today's first episode is the big picture of embodied intelligence. First, there are many misconceptions. Is embodied intelligence simply connecting GPT or Dubao to a robot? Is it just training a reinforcement learning model so robots can run and jump? Or is it training a VOA model to grab apples, open drawers, or play with walnuts? These are all part of embodied intelligence, but they're just small islands on the map. True embodied intelligence is an archipelago formed by countless connected islands. So today, let's build this big picture of embodied intelligence. Part 1. What is embodied intelligence? Embodied intelligence is the intelligence that exists within a robot's body. It's not a purely software-based intelligence floating in the cloud. It needs to truly live inside the robot's body, relying on the robot to perceive and understand its environment, then internally perform cognitive reasoning and decision-making, and finally translate into the robot's actual actions. So, how does a robot perceive the world? Robots are equipped with many sensors, such as RGB cameras, depth cameras, LIDAR, microphones, and force and tactile sensors. Together, they perceive the robot's internal and external states. This leads to 3 core concepts of embodied intelligence related to environmental perception and cognition. The first is robot perception, which gives the robot abilities like vision, hearing, touch, and force sensing. In other words, it uses sensor data analysis to achieve the robot's 5 senses. The second is robot mapping. Robots not only need to see the environment, but also to structurally understand it, like where the walls are, where the tables are, where it's passable, and where various objects are placed. This is the robot's environmental map. The third is robot localization. The robot must also know where it is right now, its own position on the map, or its relative relationship to the map. Otherwise, the robot will get lost. Part 3. How does robot intelligence act on the body? Robot intelligence isn't just about understanding the world. We also need to drive the robot's body to truly act and change the world. Robot movement can be divided into 2 types. The first is local motion, like taking a step forward, reaching out to grab a ball, or avoiding nearby obstacles. It focuses on the small area around the robot. The second is robot motion, like the classic piano mover problem, how to move a piano through many rooms to a target location. This considers the geometric structure and motion paths in the entire large space. But what's truly complex isn't robot motion, but robot behavior. Behavior usually carries clear semantics, like walking to the table, grabbing an apple, or opening a door. Behavior is typically executed through motion. For example, the behavior of grabbing an apple is actually a series of motions supporting that single action. Many behaviors combined form a task, like first taking an apple, then walking to the refrigerator, opening the door, putting the apple in, and closing the door. The robot has completed the task of putting the apple in the fridge. This leads to 3 core concepts of embodied intelligence related to planning and control. The first is motion control, such as motor control, stable walking, and local obstacle avoidance. These are local control or motion control problems. The second is motion planning, which handles the robot's global motion in complex spaces, how to find a feasible path while avoiding obstacles in a large area. The third is task planning, which involves how the robot completes complex goals through long sequences of behaviors, like making a cup of milk tea or doing something small. Additionally, robots have 3 specialized motion abilities. The first is local motion, which covers basic skills like walking, running, and jumping. The robot marathons and robot dancing you see now fall under local motion. The second is navigation, which is the robot's ability to move from point A to point B in a large space. For example, the sweeping robots and delivery robots you see solve navigation problems, not motion ability issues. The third is manipulation, which is the robot's ability to use its hands and arms to control objects, like grabbing an apple, cutting an apple, or peeling an apple. All fall under manipulation. Part 4. How does a robot learn? Robot learning essentially involves learning what to do and how to move or act in a given situation, abstracting motion skills and behavior strategies from data and experience. There are currently three mainstream learning paradigms. The first is imitation learning. It's like how humans learn. Watch an expert do something, then imitate and learn. For example, a human demonstrates pouring water many times, and the robot imitates that motion skill. The second paradigm is reinforcement learning. The robot continuously tries and errs, rewarded for correct actions, and punished for mistakes, gradually mastering the skill. For instance, a robot keeps falling down and getting back up, falling and getting up again, until it learns the motion skill of walking. The third approach is world model learning, often just called model learning. This is a very hot direction recently. The robot doesn't just learn how to act, it also learns how the world changes, how the world operates. For example, if I let go of a cup, it falls. If I push a door, it swings open. These are the rules of the world. The robot can then use these rules to perform forward simulation in its mind, deciding on the best strategy to complete complex tasks. So how should these learned skills and strategies ultimately be expressed? There are many forms. The first form is explicit code, like writing Python code to express skills and strategies as explicit logic or deep neural networks. You can use small to medium-sized deep neural networks to represent a strategy, learning an explicit mapping from world state to robot action from data. Going further, today's popular large models learn more general and versatile behavioral abilities and skills from massive internet data. Finally, there's a very important point. Robots don't exist in isolation. In the robots world, there are humans and other robots, and they are also part of the environment. This leads to two important directions. One is human-robot interaction, how robots converse and collaborate with humans, like a robot and a person moving a table together, though sometimes they may compete. The other is multi-robot collaboration, such as when someone travels and has a robot dog to carry things and a drone to take photos. So you'll see that embodied intelligence is far more than just putting GPT into a robot. Behind it is a vast technical system composed of perception, mapping, localization, planning, control, decision-making, learning, interaction, and collaboration. And today, we've only just opened this big picture.